Now we're taking a look at section 8.5, which is called partial fraction decomposition. That is a process of taking a rational expression and writing it out as the sum of simpler rational expressions. So we're going to look at 4 different cases of this, and what we're going to do is just go step by step through each case. So let's start with step 1 here. In this case, we're looking at denominators with only non-repeated linear factors. So each factor only appears once. So step 1 is to factor the denominator. So not so bad in this example. Step 2 is to write out what we want. So what we want is we want this fraction to be decomposed as the sum of simpler fractions. So if that were the case, we would need 2, and one of them would have the denominator x minus 4 and the other the denominator x plus 2. Now we do not know the numerators, so we write a and b. We know the numerators will be constants because the degree of the numerator of the original fraction is 1, the degree of the denominator is 2. They're 1 degree off. So the same should go for these over here, and that's kind of going to be consistent throughout this process. Just looking at the type of factor in the denominator. So the next thing is to multiply both sides by the LCD. The LCD will be this here. So I'm going to multiply both sides by x minus 4 times x plus 2. And of course it will get distributed over here because I have 2 terms over here. So here's my step 3. I'm distributing, it cancels over here. When I distribute it over here, it cancels differently with each fraction. So what I have now is kind of a special type of equation. This is called an identity. This is true for any value of x. We are not solving for x because we originated with an expression, so we can't really solve for x. What we are solving for is a and b. Because this is an identity, we can plug in any value of x that we want. So we're going to strategically choose values of x to solve for a and b. So first, notice that I have x plus 2 times a. So for step 4, I'm going to let x equal negative 2. I'm doing this because I will get a times 0, which means I should be able to solve for b. So every x value gets replaced with negative 2. So I get negative 6 equals, negative 2 plus 2 is 0. That was the whole point of choosing it. And then b times negative 6. Divide both sides by negative 6, and I get that b is equal to 1. We can do that one more time by checking out that b is being multiplied by x minus 4. So if I let x be equal to 4, I should zero out that term and be able to solve for a. So let's let x equal to 4. So I'm replacing every single x value with 4. Okay, so I get 3 times 4 is 12. A times 6 plus 0. Divide both sides by 6 and I get a equals 2. So I have my a and my b values now, but the problem didn't ask us to find a and b. The problem said to decompose the fraction. So your final step will always be to write out the fraction in the decomposed form. So we had a over x minus 4, so 2 over x minus 4, plus b over x plus 2. So 1 over x plus 2. So this answers the question. So if you actually added these 2 fractions together by finding a common denominator, what you would get is the original. That's kind of the whole point. So let's take another case here. What if you factor the denominator and notice that some of the linear factors are repeated? What do you do differently? Well, you can see that when you do your setup, you need to take into account the multiple factors of that linear factor in the denominator by setting up several fractions. You'll need as many as there are powers of that linear factor. So in this example, we can see that the denominator has already been factored. So let's go directly to step 2, writing out what we want. So I'm going to start with the repeated factor. So I'm looking at the original here. So I'm going to have a fraction with, or I could, we're always writing out the worst case scenario, I could have a fraction with x minus 1 in the denominator, and I could also have one with an x minus 1 squared in the denominator. That is up to the power that we have here, so that's as many as we need. We do also have an additional linear factor of x plus 2, but it only appears once. Okay, because there are only linear factors in these denominators, the numerators could only be constant, so I'm going to call them a, b, and c. Now from here on out, the process is pretty similar to the previous one. We multiply by the LCD to get rid of all the denominators. So let me do that next. So the LCD is always going to be this factored form. So x plus 2 times x minus 1 squared. Over here it will be distributed. Okay, x plus 2 times x minus 1 squared. So everything cancels on the left-hand side. So I have x squared plus x. And here I will have a times 1 factor of x minus 1 times x plus 2. This will be b times x plus 2. And this will be c times x minus 1 squared. Alright, now we go through the process of plugging in values for x to solve for the unknown values of a, b, and c. So there are two obvious choices. We want to plug in x equals 1 and also x equals negative 2. This will zero out some of the terms. So let's start off by plugging in x equals 1. Okay, so I'll have 1 squared plus 1 equals a times 1 minus 1, which is 0, times 1 plus 2 plus b times 1 plus 2 plus c times 1 minus 1 squared. So this will be 0 and this will be 0. That was the whole point of choosing x equal to 1. So we have 2 equals b times 3. Divide both sides by 3. b is 2/3. So we have our value for b. Now let's go through that again. This time we'll let x be equal to negative 2. So replacing every single x value with negative 2. So negative 2 squared plus negative 2 equals a times negative 2 minus 1 times negative 2 plus 2 plus b times negative 2 plus 2 plus c times negative 2 minus 1 squared. So once again, this is 0 because negative 2 plus 2 is 0, as is that. So what we're left with is negative 2 squared is 4 plus negative 2 is 2 equals c times negative 3 squared, 9. So c is 2/9. Alright, so we've exhausted all the values of x we could use to zero out some terms. So what you have to do now is just plug in anything for x. Usually you want to go with 0 if you haven't already used it. So I'm going to plug in 0 for x, but I'm also going to plug in the now known values of b and c. So let me write this down. Let x equal 0. I'm just picking something that seems easy. I'm also going to write replace b and c. We know what they are, so we might as well write in what they are. And then we should be able to get the value for a. So I have 0 squared plus 0 equals a, which I still don't know, times 0 minus 1 times 0 plus 2 plus b, which I know is 2/3, times 0 plus 2 plus c, which is 2/9, times 0 minus 1 squared. So once again, you can plug in anything for x. You could plug in 17,000 if you want. 0 is a lot simpler than that, so I'm going to go with 0. Okay, so let's simplify this. 0 equals a times negative 1 plus 2, negative 2. 2/3 times 2 is 4/3. 2/9 times 1 is 2/9. So 0 equals negative 2a plus, let's see, 4/3. I want that in ninths, so 12/9. So 14/9. I'm going to add the 2a over and then divide by 2. And now I have the value for a. A is 7/9. So the last thing you want to do at every single one of these is to write out your decomposed fraction. So we do that down here. So I have 7/9 over x minus 1 plus 2/3 over x minus 1 squared plus 2/9 over x plus 2. Another way you could write that, if you don't like a fraction within a fraction, is to just move the denominators down. So you could also say 7 over 9 times x minus 1 plus 2 over 3 times x minus 1 squared plus 2 over 9 times x plus 2. And that would be the same thing, it's just it doesn't have fractions in